Hello everybody. We go on with a little bit of the foundations of mathematics, the building stones of mathematics, and we talked about sets. That's really one of the most primitive building blocks you can think of, especially in modern mathematics. Of course, sets and so were only studied in the last 2 centuries or so, starting by people with counter and all that. But they were of course used, just not named that way, they're not recognized that way. And but it was also very clear that sets are too elementary a building block to just work only with sets. And there's a very other important concept that's what we call the concept of function. And you could compare it a little bit with this. If you think of a society consisting of many cities, and cities are sets of the inhabitants. But of course, just these cities on its own, that's not a society. Or what are you going to do? If everybody is in a city and doesn't do anything and stays in the city, well, in a lockdown situation, that might last for a couple of months, but clearly that's not the way to get a prosperous economy and have innovations, growth, all these things. What does it mean? It means that these cities has to be connected to each other. In other words, there are roads between these cities. And it's a bit the same imagery, you can say. We have the sets, but between these sets, we're going to now also have to have roads, namely functions. And what is a function? So we have a set A. Let's make a little bit of a diagram here. A, and then we have another set B here. I'm not saying that the A and B have to be different, but just let's put them a bit apart from each other so that we see what happens. And so there are elements in here, several elements, and there are also elements in here, most likely, otherwise we have an empty set. And what is now a function? A function takes for every element in A and sends it to an element in B. Now, I'm not saying that every element in A has to be sent to a different element in B. So, for instance, this is possible. And here, let's send this element to there. But what I cannot do is say, okay, I stop. I don't put anything, I don't say what this element goes to. Every element has to be mapped somewhere. That's what a function is. Sometimes in the textbook, all the way at the end, they discuss so-called partial functions where this is not required, but we will not really deal with much of them. So for us, a function is always every element is mapped to an element there. And you see, I'm using this arrow here because there is a direction, right? It goes from A to B and not from B to A. Of course, I could make a function from B to A, but that would be a different function. Okay, so a function has, what is a function has to do is an assignment for every element in A, we have to have an element in B. Now, often we use small letters like F and G for functions, and then if A is an element in capital A, little a, then we write F of A for the image. So this would be F of A. But note, if this is little b here, then this is also F of B. So, as I said, it is possible that 2 elements are sent to the same element. Notice there are also here elements in B that have no arrow coming in. We sometimes say there is an arrow coming in here. That's, you see what happens. In other words, they are not the image, meaning they are not, there's no element in capital A that is being sent to that element in capital B, so they are not an image. That's allowed. And we will talk about there's some special names that we will give in cases, when special cases arise. Okay, so that's our notation. It's also something that, of course, you know for ages. You have been working very often. What have you been doing? Well, we would take, right, so this is the picture, but often one denotes this this way. So the colon here means it's a function that goes from A, and there's an arrow again that indicates the direction to B. And we call this the domain of the function. And then sometimes this is called the codomain or the target. There are a couple of different names here. Normally we pay less attention to the B than to the A. It's the domain. If you think about programming on computer perspective, these are the inputs and these are the outputs. okay? Or potential outputs, I should say, because, for instance, in capital B, this is not an output. It's a potential output, but it is not being outputted by anything from this set A here. Okay, so that's the notations that we have, and for instance, we have from the reals to the reals, and you have a function that is very well known. For instance, if the function given by a polynomial, say x cubed minus 5x plus 1, that is a function because for every value, so what is f of 0, for every input we can find the output. If I put in 0, I get that. What is the function value of 1? That is 1 minus 5 plus 1, that is minus 3, and so on. Okay, so this is a very compact way of we have a formula for the function that allows me then to calculate a function in any point I want. Now, this does not mean, and be careful, that every function has to be given by a formula. Okay, for instance, the function that I have here, I'm going to make the function a little bit more precise by putting also saying what the elements on this side are. Sorry, let me suppose in capital A we have the elements little a, little b, and little c and d, and here with the elements 1, 2, 3, 4, 5, and 6. So here there is a function, but there is not really a formula. The only way that I can describe this function is by actually enumerating every input and its corresponding output. So this function would be completely described if I say f1, fa is 1, fb is 1, fc is, what was f of c? 5, and f of d, I think that was 6. Okay? And so perhaps one name that we often will use is the elements that are actual outputs are sometimes called the image of f. So I'll circle these a little bit. So they form a subset, right? Let's use some terminology that we have already. These are the actual, so these are the actual outputs, and we call this the image of the function f. And that's a subset of the codomain. Okay. So sometimes our formulas are given, our functions are given by formulas. Sometimes they are just given by enumeration. Sometimes they're given by a description. So let me give an example of a description. So so here we have in this set are the students in class, and let's call L their initial. Their first initial. Let's call it the first initial. So these are, in other words, sorry, the letters of the alphabet. Sorry, I was actually giving the function. So we have two sets, the students in the class and the letters of the alphabet, and now the map f goes from A to L and sends a student. So a student is mapped to the first initial of his name. His or her name. So here we see a prescription, an algorithm, a description of what this function does. That's very often how functions will come to us. In the case of the formulas, the previous case, this is really often, often. This is what calculus studies if you're dealing with real functions, and this is exactly the realm of calculus. The realm of discrete math is a little bit more of this type. Finite sets, remember the reals? I hope you remember these are the reals, right? The real numbers. They are infinite sets. So that's not really what discrete math does, but discrete math talks with finite sets, and therefore maps between these finite sets. This, of course, is an example of that, but this is kind of a random example. It's just arrows that are randomly drawn, so to speak. But here we have a prescription, and so it is a bit more interesting job. And by the way, these kind of things are used all the time. For instance, to determine your your email, the CityTech email, what they do is exactly that. They take the first initial and then your last name. At least that they do for faculty. I don't know what they do for students always. No, for students, I think they take the whole name, right? But for faculty, if you look at my email, that consists of my first initial, H, and then my last name, which you all still remember is pronounced as Scoutons, right? Okay. So, and so we once we have a description, we can actually work this out. So suppose here's my class A, and let's call a couple of people here. We have Ashraf is in here, and we have Imani in here, and we have Rachel in here, and we have Rory in here, okay? And more people, I'm not listing them all. Let's say it's a very small class. And here, of course, we have the letters of the alphabet. That would be A, B, C. A little bit too many to draw all of them. So let's see where everything goes. Ashraf will go to A. Rory goes to R. So let's get our R in here. Rachel also goes to R. So again, we see that this can happen. And Imani would go to I. Okay, and clearly there are a lot of letters that are not occurring here. So the image here. So what is the image? So let's call it, we call this F. So the image of F. The image of F is what is the set? Is the set consisting of A, I, and R. The first letters of the people that are in the class, the students in the class. Okay. This was a very small class, but you can do this for bigger classes, of course, and other things where this done. For instance, every student in CityTech is assigned an employer ID or whatever student ID, and that is a function. Okay, but that already gets into an interesting thing, right? So let's look at the student ID. Student ID. So that actually is a map from the CityTech students, or CUNY students actually, because I think I'm pretty sure that every CUNY student has a same type of student ID. CUNY students to I don't remember now anymore how many, 10 digits. No, is it 10 digits? I'm sorry, guys. I don't exactly know how big your student, how long your student IDs are. I think they're 10-digit numbers. If they're not 10-digit, then okay. Imagine in a new world, after Corona, we change things and we make it in 10-digit numbers. Okay, all right. So now, what is important here, though, is that two different students should not get the same number. We have seen that, for instance, Rory and Rachel both get the same initial R. That's okay for certain purposes. Of course, when if you use it to build emails, then again you want uniqueness. So this is a special situation, a situation where we do not have that two different inputs have the same output. There's a fancy word for that. This is what we call an injective, or another word is one-to-one. That's perhaps sometimes a little bit more telling. One-to-one. One corresponds to one. Injective is the official word, and that means. Let me double check. Yeah, by the way, I should say there is a typo in the textbook in the definition of this. They call this injunction. That's a typo. That's obviously absolutely wrong. It's injective or injection. If the map, the function itself is called an injection, or the map is called an injective function. By the way, yeah, another word for function is also map. So instead of function, we also sometimes use a little bit less correct word, map. So what is an injective means? Every input. No, no, sorry, I'm saying it wrong. Every output comes from a unique input. Or differently, you could also say two different inputs have different outputs. Equivalently, two different inputs have different outputs. Now, you see that I like to call these words inputs and outputs, which the textbook actually doesn't really use. They would say two different elements have different images. But I think talking about input and output is, for most of you, probably gives a better image of what goes on. So I'm going to keep using the input-output not terminology. Okay, so that is what some functions are injective, many are not. Okay, let's, for instance, okay, let's go back to our set that we had here, A, and now my B, I'm going to make my B a little bit differently. Here is my B. It has only 3 elements, and in A has 4 elements. Okay, so give me an injective. Draw me an injection, an injective map from A to B. I'll let you think a little bit about it. Well, I want you to pause and think about it, but I'm going to go on. I'm telling you, it's not possible. How is it going to be possible? Because if I want every input, A, B, C, and D, so the 4 different guys, they all have to get 4 different outputs, but there are only 3. Okay? So, no injective map from A to B is possible. Because the number elements of A is strictly bigger than the number of B. So that is a kind of, if you want, an obstruction. So if this means that if the number of elements in A is bigger than the number in B, then there is no injection. Let's do the contrapositive of this statement. Okay, I'm not going to write it down, so I want you to do this in your head. Sometimes you have to practice a little bit. So let me make the statement again. What have I just said is that if the number of elements in the domain is strictly bigger than the number of elements in the codomain, then there is no injective map. Let's do the contrapositive of that. Remember, the contrapositive is you switch the hypothesis and the conclusion, but you take their negations. So, if, I'm going to go one more time, if, I want to do this without writing, just to practice this, but if it's hard for you, write it down on a paper, but I'm going to try to do it without writing, okay? If the number of elements in the domain is bigger than the number of elements in the codomain, then there are no injective maps or functions. So now, the contrapositive, if there is an injective map, then the number of elements in the domain must be at most the number of elements in the codomain. So, if there is an injective map, that's a little shorter word for it, from A to B, then A is at most the number of B. Because for every element in A, I had to choose a different element in B. So I had to have at least that many elements in B. So of course, in this particular example here, sorry, the A and B here, this is a difference A and B, right? The A and B is where this works. In this particular case, it's not possible, but can you make a bit, therefore, can you make a, and in fact, it's actually even only if. You can always make an injection if you have less elements. So can you make an injection from B to A? Yes, from B to A I can make one. For instance, 1 goes to A and 3 goes to B, and let's make 2 also to go to B. Oh no, I need to make an injection. Okay, that was not correct, right? So that was not correct. So what I had to do is send 2 to D. I have to send every element in B to different element in A. So this would be an injective. This would be an injection that I just pictured. And see, the arrows are important, right? Because now this is a map from B to A, the map that I just draw, and not from A to B. Okay, so that's injection. Now there is something very similar here. Let's think about something else here. Suppose we let's look at the example of a scheduler. And so what do we have? We have the courses at CUNY courses, CityTech courses, on the one hand, and the other hand we have the faculty. Sorry, it's the other way around. Yeah, okay, this is the two sets. Let's call the two sets there like this, faculty here, okay. Let's call them C and F. Now, what does the scheduler do? A scheduler, what does it do? It's a map that sends to every course a faculty member. So there's a map from C to F, which to a course assigns its instructor. Instructor of course. Okay, so for instance, the course that is called section, what's our section number here? I forget our section number. I don't think I'm going to be able to pull it up right away, so I'm just going to call this discrete mat 1 here. Oh, okay, I probably can. I'm going to cheat and find somebody's email, and then I can know exactly. Sorry. Oh yeah, what's the schedule number? Nobody knows this. Okay. I think it's OL49. Okay. So here is the class that is officially called OL49. That's our class. OL by mean online. Okay. 49, and then here are all the faculty of. Oh, sorry. What am I trying to say here? I'm sorry. I got so distracted. I made this. I said this is the class. No. OL49 is one of the elements of this set of courses, right? So this is C, and this is F, and one of the elements in here is a guy called in his own native language Schoutens. Okay. So Professor Schoutens, he has been assigned by the bursar, by the administration, well, by its chair, actually I asked, to be assigned this course. This is how it goes, okay? Now, this is a map because every course has to have an instructor, otherwise what are we going to do? Just everybody sits there in an empty virtual room or just doesn't do anything? That doesn't work, right? So, that's just an example of a map. Is this an example of an injection? Well, I can answer you this. There is a course called, give me some time if I can find the number of that course. Okay, the course number is OL54. OL54 is a course, and guess who teaches it? Me. This is discrete mat 2. So next semester, hopefully, you're going to be in that course, and I hope to be then your instructor again. So no, this is not an injection. So not injective. In fact, most of us teach 2 to 3 courses every semester. So definitely not injective. Now, what this normally does, it's not really true, but okay, there are some exceptions, but these exceptions are because of, I'll explain later a little bit what the exceptions could be, but if you would think of it just in a normal situation, you would say, well, you guys professors, you're getting money to do all this for us, so I'm assuming everybody is at least one course, right? So, okay, let's say that's not the case. As I said, there are exceptions because some people have so-called release time, or are on leave, or have administrative duties that it takes instead of teaching. But that's kind of, let's say, regular faculty. So regular faculty are expected to teach at least one course. Most of us, as I said, 2 or 3 courses. So this function has an other property, namely that every output, so here is Professor, I don't know, is there another famous professor you want to be in there? So I'm not going to name names because then I don't want to put my colleagues on the spot here. But okay. So what we want is every instructor should have at least one course to teach, and I said most of them will teach more. In fact, that is the expectation. This is the rule that we all have to do. So, what is this property? This is called a surjective map, or a little bit perhaps on a more telling is the name onto. Its surjective means that every element in the codomain is an output. That means is an image of an element from the domain. So onto, it's like every arrow that, so pictorially this looks like, let's look at an example of an onto map. So I'm going to make an onto map here on this guy. Okay, so let's make an onto map on this guy, and the reason that I do it on this guy is, we'll discuss it a little bit, but let's do it. So A goes to 1, B also goes to 1, C goes to 3, and D, well, if I want it to be on 2, then I have no more choice here. Then D should go to 2, because every single element here has to have at least one arrow coming in. Some of them could have more arrows. That is not what I'm saying, that it has to be exactly one. We will talk about that. But so this is an example of a surjective map. So let me erase a little bit what I said here. So this is a map that is I don't want you to be misled by what is written here. This is surjective map. And so pictorially you see this because, oh, this guy went ribbit to B. Okay, so this is an surjective map. Pictorially you see that because in every point in the codomain B you have an incoming arrow. Okay. And let's think about what this means for the cardinalities. What do you think? This is what this means, right? If you have a surjection, well, that means that you have to have at least as many inputs as there are as the possible elements, because every possible output is an actual output. Therefore, that must come from an input. Okay. Now, notice what is not allowed, by the way. So, we talked about maps here, and this is a map. I want to give you of something that is not a map. What do we do here? Why is this not a map? Because now, this input, the little a, that's my input. What's the output? The problem is, it is either 1 or 5. It's ambiguous. I don't know exactly what the output is because there are 2 arrows going from. So this is not a function. So 2 things cannot happen in a function. This cannot happen in a function, namely that one input has 2 different outputs. Another thing that cannot happen, so let's do away with this guy and say, okay, fine, okay, all right, I'll take it away. Now, the result that I show here is also not a function. Why not? Because now we have a guy in the domain that's not an input. But everything in the domain has to be an input. Every element in every input, let's say, well, okay, sorry. Let me rephrase it. Every input, every element in the domain has to have an output. But here, this C doesn't have anything that goes to 5. Or it goes to, assigns a number to it. Okay, so there are violations of being a function. Now going back here, so that means, yes, my argument here that B had to be at least A is because, okay, these are the number of outputs that I have, 3. Each of them must come from at least one input, but there could be for more inputs, right? But every input can only go to one output. So that's the reason why we have this inequality. Okay, so that's an example of a surjective map. And then we have the final thing is a bijective map. And that means that it is both injective plus surjective. So what does that mean? So in other words, if we have a 2 element here, let's make A and B again, kind of similar as before. This is little a, little b, little c, little d. But you'll see what I have to do here. I have no choice. I actually have to have the same amount of elements. Why? Well, because remember, a surjection meant that you have this inequality, and an injection means you have this inequality. So if they're both, they must be equal. Yeah? So injection, if you have an injection from A to B, then this means that A and B have to have the same elements, because every input has a unique output and every element is a unique output. Okay, so that's a very important property. And that's a very important concept also, the concept of a bijective map or a bijection. Sometimes also called a one-to-one and on-to, because remember, injective we called one-to-one, and surjective we called on-to. I think the textbook also, sometimes there are other, let me see if it uses, they also sometimes call it a one-to-one correspondence, which I don't like much, because one-to-one actually just means injective. The correspondence part is supposed to then say the other thing, but it's a very commonly used term, but I'm not very happy with it. So I prefer to have bijective map. Let's look at an example of bijection that we have encountered. If you try to remember of these things, was this scheduling thing? Was this scheduling here in a bijection? No, because we know that there were, like for me, for instance, I taught 2 different courses. Okay, so that's definitely not the case. What about, well, all these maps here? Is this an injection? No, because it's not injective because of that. Sorry, is this a bijection? It is a surjection. Sorry, is this a bijection? Well, it is surjective, but it's not injective. Well, it cannot be a bijection. Why not? Because there are 4 elements here and 3 there. Remember, for a bijection, you have to have the same elements. Was this a bijection? No. Right? Because there were a lot of initials that were not hit. Again, one simple reason why this cannot be a bijection, there were 4 elements here and the 26 there. So it cannot be a bijection. Was this an injection? No. Was it a surjection? No. So this was hardly editing. Very often maps like this are, it's not going to be injective. They're different. For instance, a root of this polynomial, I chose a random polynomial, so that's very hard to find the roots. But roots of a polynomial, that means, what does that mean? To be a root of a polynomial means that the value of that root is 0. So these are the elements that have output 0. But very often we know that there are many roots. Again, so not injective. These maps tend to be quite often, well, I shouldn't say they're always surjective, but I think this particular one, let's see, yeah, this particular one, no, this particular one is not, sorry. No, this one is, sorry, this one is. How do you see this? Well, you would have to take a graph of this function and then see what are the possible outputs, okay? But we had one, and where is it? Here. Ah, here, this is the one that I'm talking about. This was a bijection, right? It's not only that every CUNY student had a different, no, sorry, this is not true. But because there are, there are, of course, student ideas that are not used yet, and therefore there's no student that corresponds to that. Sorry, that's what I said was wrong. But there are, of course, a lot of bijections that happen often. There is one very, very important one, although it's so trivial that you kind of forget about it. So this is called the identity map of function. And it is a map from A to itself. And there are many ways of denoting it. The textbook likes to denote it by IA. I like to write it as 1A, so I'm going to write it as 1A. And what does the map do? Well, it sends an input A. So what is the image? The image of A is just A itself. In other words, it doesn't do anything. But that's a bijection, right? Think about it. It's surjective because every element is equal to it, comes from itself. Every element is an output because the input is itself. It's an injection because, of course, 2 different elements are different. Therefore, their outputs are different. So this is a clear example of a bijection, and there's a bijection that we have between on a set itself. So very often we look for bijection in a set. Here's another bijection of a set. Let's say that A, B, 0. No, sorry. We'll talk about this particular one later. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, 11 and 12. These are the hours. Let's call it H, therefore. So these are the hour sets. And here's the bijection. At 3 hours. Let's see what does the bijection do. So where is 1 sent to? Now, so I haven't used this yet, but I'm going to use another notation. Notice that, let me erase this a little bit. So we used an arrow to denote the fact that there was a function from the domain A to the codomain A here, and to say that an element little a is sent to another element. So let me do it here in the general original definition here. So instead of writing that f of a is 1, like in this example, okay, so let's go back to the function that we had, right? So that it is the function that we have here on the left here. So instead of writing f of a is 1, I can also write that a is mapped to 1. So it's the same thing. I have an arrow, but the arrow starts here with this little vertical strip. Okay, sorry. That's not helpful. Let me make it. I wanted to make it bigger, so let me make it bigger here. So we would write this as a maps to 1. So we have the arrow part, but we have this this tail of the arrow is a vertical, small vertical line. To make the distinction between a function where it's just a single line, a single arrow, okay, and the map. So here, so we would say 1 is sent to at 3 hours. So if it's 1 p.m., then it becomes 4 p.m. on the clock, right? It's on the clock. It's this kind of thing that you, a 10-year-old, will say, okay, guy, what time is it now? And so in 3 hours you have to go to sleep. And he says, oh, when is that? When is that? When is that? So it's okay. So assume it's midnight. It's New Year's Eve, and for 1 reason the kid can stay up for 3 more hours, although it's 10 o'clock. It's way past his bedtime, but because New Year's he can stay up 3 more hours. What is that? If I'm not doing all the other ones. What happens here? Well, 13 hours. Well, in European time taking 13 hours exist. That's military time, you would say. But let's say just American time. What would this be? 1 o'clock, right? It would be 1 o'clock, 1 a.m. But forget about the a.m. p.m. The clock would, if you look at the dials of the clock, would stand at 1 o'clock, 3 hours later. So is this a bijection? Yes, this is a bijection. I want you to think a little bit about it. But of course, if I add 3 hours to 2 different times, I get the result is 2 different times 3 hours later, right? And any particular hour is an output, namely, go 3 hours back, take that time. That's exactly what you get then. Now this tells me the principle that how I solved to show, for instance, that 2. So is 2 an output? What do we do? Well, go 3 hours back. That would be 11 o'clock. So 11, and then you see. So I subtract 3 hours from 2 o'clock, and then it's 11 o'clock. And so this map, the map that I have here at 3 hours would now send 11 to 2, right? So this is a very important thing. If I have a bijection, then in fact I have also a map, a function the other way. In other words, I can reverse the arrows. So I'm going to do this here in red. So these are the reverse arrows. So, okay, so we had our function f. And so what is this reverse function? Let's call it g. And we can only do this with bijections. I want you to think about it. Why can I only do this by injections? Okay, but before I go on, this G is called the inverse, because what it is you invert all the arrows. Inverse of f, and this is often denoted as f minus 1. Now be careful, this is not reciprocal, but it is inverse. In calculus you have seen these things, the inverse of a function. On your scientific computers, calculators, you have often a bottom like tan inverse, tangent minus 1. That meant exactly that, the inverse tangent. Okay, remember this whole thing about inverse functions you saw probably in pre-calculus. And this is what happens. But this only works really for bijective maps. Let's see what goes wrong if I try to do this here for this map, for instance. This map is on 2, was surjective. In other words, every instructor was teaching a course. The problem is that most instructors are teaching several courses. So there's no way for me to revert the arrow. I have to make a choice. Remember, an input can only have there can only be one output. So if I reverse both these arrows, then I would have, this input would have 2 different outputs, which is not allowed for a function. Okay? This was for an injective map. Here's an example of an... okay, here's an example of a map that was... yeah, no, that's not what I meant to say. Here, no. I want an injective map. No, I don't have an injective map here. All my pictures, all my injective maps have gone, but okay. I had convinced yourself that it's also not possible if you just injective. Okay. So that's the inverse of a function, and so the important thing is that the inverse, that if you have a bijection, then you have an inverse. So sometimes when instead of saying bijection, one says also an invertible function. Okay. Right. Let me see. I want to make sure that I'm not forgetting to tell you important things. There's a lot of stuff also here in. Okay, that and that I will have to still talk about. Okay, so let me go up here. Okay, so we just introduced, so if f is a bijection, then f minus 1, so if f is a bijection, let's call f a bijection from A to B, then f minus 1 will be also a bijection, by the way. Because if I inverse the arrows, of course, it's still a bijection, right? Is the inverse, which is also a bijection, automatically. I hope you're convinced about that. Okay. But nonetheless, if you have a map like this here, like let's look at this example of the scheduling or instruction, assignments of instruction. I would sometimes, it's very nice to know, for instance, what are the courses I'm teaching? So what we need to do for that means I'm given a certain output. What are all the inputs that it has? Okay, so that is called sometimes the inverse image of an element. So so let me write that. Where am I here? Okay, so I'm going to erase a little bit this thing here that I can use this here. So we have this f here, and I want to talk about the. So you see here that if I take the inputs that have outputs me, that is OL49 and OL54. I'm not teaching anything else. How do we notice? The notation is, and this is a little bit perhaps confusing, is I'm using the -1 also, but applied to a given element. So I agree, this is misleading and it can cause confusion. It is such an standard practice for many centuries, I would almost say. We have been centuries, a bit exaggerated. For many decades, we have been using these notations, and so it's sometimes a little bit unclear. When I write f to the power -1, do I mean that is the inverse function, and therefore f is bijection? Not necessarily. I could. So, for instance, we already argued that this f -1, it as a function itself does not exist, because I don't know. As a function, it should send every instructor to a unique course, but there are several courses he teaches, so you have to make a choice if you want to make this into a function. So here f minus 1, it does not denote a function, but it's an operation that given an output gives me all the possible inputs. It is it's such a useful notation that we need to keep it. Okay, so that's what we call the inverse of an element. So what else do we have to talk about? Now, going back to our bijection, this has to do also with something very important, but I'm going to talk more in generally. Suppose we have a function from A to B. Okay, so sometimes instead of writing f colon here, I also would just put the f on top of here. So okay, so let's look at the example that we have here. A, B, C, and D. A goes to 1. Let B also go to 1, and I'm going to do really weird. I'm going to send D also to 1. I'm going to send C to 2. Then 3 gets nothing. Okay. Now, I also want to make a function B to a new set C. And let's call that function little g, because it's a different function, so I should give a different name to it, right? So my set B is still the same. It's 1, 2, and 3. And C is the set of English words. Okay, and so what is the map that I'm going to do? I'm going to send the element 1 to the word 1, the element 2 to the word 2, and the element 3 to the word 3. So 1 goes to 1, 2 goes to 2, and 3 goes to 3. Now, be careful, right? Here, 1, 2, and 3 were numbers. On the right-hand side, they are words. So it's not identity here. We both pronounce them as one, the left-hand side and the right-hand side, but they are different things. On the left-hand side, we have the natural numbers, or part of the natural numbers. On the right-hand side, we have all English words. Of course, there's another English word here. The word is fight. That's an English word, right? So that's there, and there are many, many more. Okay. So I'm just wanting to make sure that you see that it's not just numbers, that the English words of English numerals, but it's every English word is in the right-hand side and C. Okay, so what can we do now with the F and G have one thing in common though, namely this B. And so what I could then think about is, okay, so I think of F as a subroutine that takes input one of these letters, little a, b, c, and d, and sends it to the numbers 1, 2, and 3. I don't know why I did that, but that was just a random choice. The next G was a little bit more smart. It sent a number to the name, its English word, the English name that it would have. Well, what if I combine this? So, what I want to do there, therefore, is concatenate my arrows. So let's do this here. So I'm going to draw my C again here. So this 1 here will go to the word 1. This 2 will go to the word 2. This 3 will go to the word 3. And I assume that B has no more elements. So this is the end of it. But again, remind you, the word light is also there. And plight and right and night and everything else, and not all the things that rhyme on "ite," of course. Okay, so what does this now give me is what I could look at the composition. So the composition, what is the composition is where you go from the first to the second and from the second to the third. Okay, and this is denoted, and this is a little bit weird, this way. You say, Professor, you wrote it in wrong order. No, I didn't. Because look at why. I want to write G of F of little a. Let's calculate what this composition does with the input A. Well, the only way to do this is break it down into the two processes. Namely, first I find what F of A is, the image under A. That is this part of the arrow. And then I go to this part of the arrow, and somehow my arrows were gone. Okay, so this is what we would write this way, right? It's G of f of A. And that's why the order is G compose F, G after F, rather than the other way around. Okay, so what is that? F of little a was 1, so this is G of 1, and G of 1 was the word 1. Okay, so G of f of A sends little a to 1. So let's now write it down a little bit with arrows. So this is G of f, right? This goes to 1. Where does little b go to? Where does little c go to? And where does little d go to? 1. Because little f of a, f of little a is 1, and G of 1 is 1. The word 1. Okay. C also goes to 1. Where does D go to? Oh, no. C goes to 2. Sorry, C goes to the number 2, and then the number 2 goes to the word 2. So 2. And it's D that goes to 1 also. So that's how you form the composition. So composition is basically putting one arrow after the other. Now there is a condition here. So in order to write this down, you notice that this is the condition, right? So we had A from F to B, and we had G from B to C. We needed that they have this common, the codomain of F should be the domain of G. Otherwise you cannot compose. Otherwise you cannot, the arrows do not connect. Okay. Now, going back to our inverse functions here, let's see what happens. What is G compose F? I can do this here, the composition of two functions. They don't need to be injections, don't need to be anything. Any function I can compose, any two functions I can compose. But let me do this now in the very special case where F is a bijection and G is its inverse. So we are now inside in this picture again. Let's see what happens to the element little a. Little a, this is a new map, right? It's not the same as the previous one. That's G of f of a. Now, f of a was 1, right? This is the element 1 here. So that is G of 1. And what did G do? Well, G sent it back. Is a. So G compose f sends an element to itself. Because, why? Because f takes the input, sends it to the output, and the inverse says, oh, go back. So the result is, so G compose f is just the identity. Remember, this was this very, like, almost silly map. Where did it go? I probably erased it in my... here it is. It's just right, it's right there, guys. Why didn't you say anything? Probably you were screaming, Professor is there, Professor is there. Here it is, the identity map. Okay? And even nicer, so this, remember, so F goes from A to B, and G goes from B to A, and they had this common B here. But they also have the common A, so I could also form, okay, let me get rid of this picture, I don't want my definition. So I could also form F compose G, first to G, first the red arrows, so this way, and then go back. What's the result? The identity map, but which one? The one on B now, right? Because now we start from B and we go back. So we start from the outputs, we look for the input, and then we take again the output. Of course, we didn't do anything. So that's the identity. There's of course something that you've seen in calculus as well, or in pre-calculus. The inversion function is exactly that. That if you compose them, they cancel each other out. Like logarithm and exponential function is a very good example. And that's often used to solve equations, right? And same for if you know that the sine of an angle is 5, that's not possible. The sine of angle is 1/3, then you can find what the angle was by taking the inverse sine. It's a bit more complicated because actually sine is not an injective function, so we have to manipulate a little bit, and that's why we restrict the domain of the inverse function. That's the reasons why we have to do this. I'm not going to go into that. That's not what we're going to bother ourselves with here. So, a very important, therefore, what I'm saying is when you have a bijection and you compose it with its inverse, either way, in either direction, you get the identities. Okay, and that's all what I wanted to say about this, and I wanted to show The graphs of functions, I'll let you read you about that, but I want to talk about two functions that we will use quite a lot, and these are the floor and ceiling functions. So the floor function is a function from the real numbers to the integers, and same for the ceiling. Because it's very useful to sometimes, since we do discrete math, we normally only work with integers, just discrete counting numbers. But real numbers are not discrete. They are between any two numbers, another real number. In fact, even the rational numbers are not discrete, because for the same reason, if I take two rational numbers, I can always take their average, and that's an average natural number in between. So to go from these more weird things that are not really part of the realm of discrete math, to get into discrete math, we will use these two floor functions and ceiling function. And what they do is they are rounding function. They are sometimes also, the floor is called the largest integer. Yeah, okay. Let's see what the floor does. So the floor is denoted like this, floor of x, and the ceiling is denoted like that. Now, rather than explaining exactly the definition, let me do it on examples. The floor of 3.14, of pi in other words, or 3.14, what is that? It's the smallest integer that is below it, so that is 3. Okay, so floor is, sorry, I said smallest, this is the largest. Largest integer below it, below the given number. So what is the floor of 3? Well, below we mean that 3 is below 3, right? So that's 3, of course. Okay, I hope that is okay. But this is, it gets a little bit weird when you're dealing with negative numbers. Not that we're going to do this often, but it's important that you see this. Minus 5.3, what's the floor of that? Now you might be tempted to say minus 5, but let's look at the real line. If we would make pictures, here is minus 5.3. Okay, so what is this? Here is minus 5 and here's minus 6. What's the one below it? This one. So the floor of minus 5.3 is negative 6. Okay, now what's the ceiling does? The ceiling does the opposite, right? So the ceiling of 3.14 would be, the ceiling is the smallest integer above it. So the smallest integer above 314 would be 4. That's, we would say, rounding up, right? What's the floor of 3? Sorry, the ceiling of 3. The ceilings are denoted with the ceiling, right? I hope the notation kind of, oh, I had one, my ceiling had a little bit of floor also. Okay, what is that? Well, of course, that's again 3, right? That's the smallest integer above 3. 3 itself is an integer above itself, so that's okay. And so here, rounding up, this is perhaps a little bit easier to understand. If you don't round up minus 5.3, you get minus 5. Same reason, right? It is this minus 5 that is slightly above it. Okay, so these are two functions we will see quite a lot. There are a couple of rules of that, and I don't want to deal too much with these guys. Another one that we often use is the factorial. So the factorial is a map from the natural numbers to the natural numbers that sends and is denoted n factorial, and the definition is the product of all the numbers all the way up to n. So for instance, 3 factorial would be 1 times 2 times 3, that is 6. And these numbers get quite big very quickly. Around 10 factorial, 20 factorial already is million, billion, trillion, quadrillion, quazillion, gazillion. It's already a number with 3, 6, 9, 12, 15, 18 digits. So 20 factorial is an 18-digit number. I mean, I'm not saying this is a rule. This is just by calculation. So this is a big number. So and this is only 20 factorial. So imagine 200 factorial, 1,000 factorial. There is a couple, you could discuss this a little bit, but there's a convention to call this 1. You say, well, shouldn't it be 0? Notice that we always start from 1, right? If I would start from 0 in n factorial, of course the result would always be 0, so that was silly. We're never going to do that. So we always start from 1. But 0, you cannot start from 1. So we have to give a value to this, and we declare it actually really to be 1 if you want. There are arguments that for it to be correct. In fact, in discrete math and also perhaps in statistics, you have already seen that the factorial is the number of permutations. Okay, what is that? A permutation of a set is nothing else than a bijection from the set to itself. So if A is a set of n elements, then the number, sorry, I told you I'm gonna, the number of bijections from A to A, that number is exactly n factorial. The number of bijections from A to A. Okay, so we look at a set of all bijections. Remember, this is how we can build sets, right? By declaring the universe is all the functions, and now we declaring it has to be a bijection from the given set A to itself. That is called a permutation, and I'm claiming that the number of permutations n factorial. I'm not going to prove that. I'm going to just tell you that is the case. So what is, if I go from the empty set to the empty set? We haven't done this really yet. So can there be a map from the empty set to the empty set? And the answer is yes. There is one map, namely nothing. If you want the identity, but what does a function has to do? Is this a function? Well, what you say? What? There's nothing there, right? Exactly. So the empty set itself is a function from itself to itself. That gets weird that way, right? Okay. So what I mean is, well, the conditions for this to be a function is that every input has to have an output. That's the case because there are no inputs. Remember in our logic thing, this was called a moot. If you have to say something, if you make sure that a certain property is guaranteed by a bunch of elements, if there are no conditions, if there are no elements to be conditioned, then it holds trivially. And another thing that a function has to do is that every input has to have an exact unique output. But again, there are no inputs, so this question again is moot. So there is one map from the empty set to itself. It's obviously a bijection because injective. Why is it injective? Well, if it would not be injective, you would give me two inputs that have to go to the same output. There are no inputs, so that you cannot give me a counterexample. Can you give me a counterexample that this is not surjective? That would give me an element in this codomain that has no incoming error. But there are no elements in this codomain, so there's again a moot statement. So there is one element, one bijection from the empty set to its empty set, and therefore, remember that the number of bijections from a set to itself is equal to the factorial of its cardinality. Well, this has 0 elements, so 0 factorial has to be equal to the number of bijections, and that is 1. I know, this might be really, this is how crazy mathematicians sometimes are, but believe me, it makes a lot of statements nice and coherent. In particular, all of you that have done Calc 2 have seen that this is that it's very useful to have this 0 factorial when you talk about Taylor series, etc., etc. Okay, I'm going to stop here. There's quite a lot of definitions, but nothing is hard, and so the homeworks are going to be just a little bit checking all of the definitions.